So energy expression was E equal to n square h square 8 ml square. See, this is the expression for energy. Applying Schrodinger's time independent wave equation to a particle in potential well of infinite height, the particle is under consideration. So now we got the expression for energy as En is equal to n square h square by 8 ml square, where n is an integer, that is 1, 2, 3, 4. So if the particle is in the state n equal to 1, refers to the first state. We call this particular state as 0 point energy. And when you look at the E, then E becomes E1. You know that from the expression that h is nothing but the Planck's constant, m is the mass of the electron, L is the width of the potential well. So now even an electron in the lowermost energy state has got a certain positive value for the energy. So the electron sitting in its lowermost energy state, that n equal to 1, has got the some a definite positive value for energy. So it is not zero. According to classical mechanics, the energy of the particle sitting in its lowermost energy state will be zero. But according to quantum mechanics, it is not zero. It has got certain minimum energy. So now when you go to the second level, that is n equal to 2, we'll get E2 is equal to 4 times E1. And you got, when you go to the level 3, it is 9 times E1 and so on, you know that. Okay, see that the E2, E3 and E4, they are 4 times E1, 9 times E1, 16 times E1 and so on. And for all the states n greater than 1 are called the excited states. N equal to 1 is called the ground state, that is lowermost state, and all other states greater than 1 are called the excited states. So when the particle sits in the lowermost energy state, we call it as 0 point energy. 0 point energy is a consequence of Heisenberg's uncertainty principle. For example, if you assume that the particle got energy 0, okay, then what will happen? E equal to 0, E equal to Pc, therefore momentum also becomes 0. Since E equal to Pc, if you substitute for energy, if you say that energy is 0, certainly then momentum is also 0, because C is velocity of light, so momentum is also 0 in order to balance the equation. If you say the momentum is 0 from de Broglie's wave equation, lambda equal to h by p, the p is, then I can write as p is equal to h by lambda. So lambda is 0 here, so something divided by 0 gives you infinite. It means if the energy of the particle sitting in its lowermost energy state, if say it is happens to be 0 as per some assumption, then the wavelength of the particle will be infinite. This is not at all possible, isn't it? So wavelength of the particle cannot be infinite. In such a case, if you say that lambda is infinity, then the particle cannot be confined to the box. Hence, a particle must have a minimum amount of kinetic energy. I'll summarize what I said. See, we have seen that the particle can exist in different energy levels. Look at the diagram, right side. So the n equal to 1, 2, 3, 4, 5, 6, like that on the right hand side. And the left side, it represents the probable energies. If the particle is in first state, it is E1. The particle in second state is 4 times E1. The particle in third state, 9 times E1, so on. So if the particle, that is according to quantum mechanics, what it says that the particle sitting in its lowermost energy state should have a minimum energy. So it possesses minimum kinetic energy. According to classical concepts, it can be 0. It is not possible according to quantum mechanics because of the uncertainty principle. You have seen that lambda goes to be infinite. That's not at all possible. Okay. So now the next thing you have understood that we got the expression for the wave function. So we call here it is psi n is equal to I square root of 2 by L sine of n pi x by L. So this is the wave function for the electron in any state where n is equal to 1, 2, 3, 4, 5, like that. Okay. So this is a general wave function. It's called the normalized wave function for the electron in the state n. If you say that n equal to 1, again this is psi 1, I equal to root 2 by L sine of pi x by L, like that. So if the particle is in the second state, it has a different wave function that is represented by psi 2. If the particle sits in the third state, that is n equal to 3, it has got a different wave function, and so on. And see, it is seen that we already understood that the wave function psi is nothing but a complex number. We can't observe because of y. We will not be able to visualize. We will not be able to practically, and the physical world will not be able to observe. Therefore, we take the conjugate of that and multiply that by the psi, so we will get the modulus of psi square. So that is called the probability density. You know that. So the probability density, it is defined as it is the likelihood of finding the particle in the given region of space at the time at the given time is proportional to modulus of psi square. So you have seen that the wave functions are different. If that is psi is different if it sits in the different energy states. So it is psi 1, psi 2, psi 3, psi 4, etc. like that, depending upon the uh, particle sitting in the different state. Then it's certainly the probable values psi 1 square is nothing but it is psi 1 square, psi 2 square, psi 3 square, psi 4 square. They represent the probabilities of the particles sitting in the different energy levels. We'll see that in this diagram I have drawn the wave function psi. Psi, and you look at n equal to 1 left hand side, n equal to 2, n equal to 3. So they are the wave functions. See here the wave function can be both positive and negative. So cannot expect, but you cannot expect the probabilities to be negative, isn't it? So and the middle one. Say if the particle is in the first state, the probabilities of the particle can be given by this the curve. Look at in the middle second one. So you got two ups, that is psi 2 square. In the third state n equal to 3, you got 3 ups, and that is on the positive side of the so these are the probable values for the particles sitting in the different energy states. Okay, so now when you look at the last third column, that is third diagram. So look at the energies, how they have been occupied. See, they are not so the E1, E2, E3. Say you don't have the same space between E1 and E2, or between the two E2 and E3 and E4 and E4 like that. So they got different spaces. They are placed at different heights because it is 4 times E1, 9 times E1, 16 times E1, and so on. Okay, so this is how the energy levels have been split, distributed in the various energy levels in a particle. Okay, what you had in the first state, that is with respect to the probability, if you look at the wave function psi 1 and the probability of finding the particle psi 1 square, both are same, and you got the probability is maximum at the middle of the this potential well. See, the distance is 0 to L. So now if the particle sits in the ground state, that is n equal to 1, then probability of finding the particle will be maximum at the middle of the box or the middle of the potential well. And as you go towards the boundaries, the probabilities decreases and becomes minimum at the boundaries. So if the particle sits in the n equal to 1 state, the probability of finding the particle is maximum at the center of the box. Okay, and it is almost 0 at the boundaries. If you recollect the second, that is modulus of psi 2 square, that is probability of finding the particle in the second state, the wave function is psi 2. The probability of finding the particle in the second state, modulus psi 2 square, we'll see that if I want, I'll go back. See, look at this. You have seen the diagram. See that the probability of finding the particle is maximum at L by 4 in the second. Okay, and it is maximum again at the 3L by 4. But you don't have the probabilities at L by 2. And see that in the third, that is particle in the third state. So they are at different positions. So what you observe that if the particle is in the ground state, the probability of finding the particle is maximum at the middle of the box. At the center of the potential, you have the probability. It means more probably you will find the particle at the center of the box. And it is very less probability at the edges of the well. If you take the second state, the probability is maximum at L by 4 and it is again maximum at L by 4, but it got the minimum at L by 2. For n equal to 1 state, probability is maximum at L by 2, but n equal to 2 state, probability is 0 at L by 2. See that? Okay. So now, according to classical picture, the particle can be found anywhere within the well, isn't it? According to classical picture, the particle can be anywhere between x equal to 0 to L. There is no such probability for certain values at any point. Here, the probability is same. It can have any value anywhere between 0 to L. But it is not exactly the case in quantum mechanics. You see that it is maximum at L by 2 for n equal to 1, and it is maximum at L by 4 and 3L by 4, n equal to 4. But that is 3L by 4. But it is not the case for a classical object. Okay. As you go up and up, as the state increases, n equal to 1, 2, 3, 4, 5, 6, etc. So you will see the more peaks. So at n equal to 1 state, you got only one peak, and n equal to 2, you got 2 peaks, n equal to 3, you will get 3 peaks, and so on. So it represents a quantum number. As you go up and up and up, as n is increases, it ultimately reaches the classical distribution. Okay. So now, what you understood so far? So, with respect to classical results, you said the classical particle can have only can have any positive energy between 0 to L, any value, any positive value, and even it can have zero values, any value 0 to and positive, but it is not specified according to but according to quantum theory, these values are specific. They got the discrete. Okay. In classical picture, any value can be any value 0 to 0 and positive, any value. But according to quantum mechanics, these values are fixed. You have seen that E1, 4 times E1, 9 times E1, 16 times E1, and so on. And from classical picture, the minimum energy can be 0. The minimum energy can be 0. But according to quantum mechanics, the minimum energy cannot be 0. It has got certain positive value that is called the 0 point energy. Okay. When you join the ends of this here and this one, you will get a circle. So this looks to be s orbital. Look at the above, the second one, you will get something like this. When you join these two, you will get, so it will become p orbital. In the third case, you will get something like this. So this is the d orbital like that. So the distribution of particle, and I'll draw one more. See here on the same screen. See here, if the particle is in this state, here it is going like that, and it will make a with this standing waves. So you call this is A, and this side is B. Okay. So now what I do, I join A and B. If I join A and B, how do I see that? I'll find something like that, and center is nucleus. So this point is here A and B. I'll rewrite this. Understood now? Oh, see, what I am doing is, so if I join A and B, so we call this A and B. I joined A and B. You got a center. Imagine this. This is the nucleus, and when it is joined, this is how the electron is going. This is called the Sommerfeld model. Okay. So what the model we have chosen is a theoretical model, is in comparison with the electron going around the nucleus. Okay. That's how it can be understood.